Hi, my name is Ansh Gupta. I'm from Team 26929 Pioneer 1. After watching today's video, you'll understand what is odometry, its applications, and how it can help you and your FTC team win more competitions. Also, this is part 1 of a larger 3-part series, so after watching part 2 and part 3, you'll understand the math behind it and how you can apply it in Java for your teleop and autonomous. So, let's not wait any further and let's get right into it. First off, looking at the Odometry series as a whole, in part 1, we'll look at understanding odometry. We'll look over the concept behind odometry, the applications of it, and how you can use it in FTC. Then in part 2, we'll look at how you can specifically use odometry in teleop. So we'll look at the math behind doing field-centric drive control. If you're not sure what that is, I can promise you're gonna love it. Then we'll look at coding in Java in either Android Studios or on-bot Java. Then next, we'll specifically look at how you can use odometry in autonomous. So we'll use the same math from teleop to create a motion planning system. Here we'll also look at how you can use Java to code this system in both on-bot Java and Android Studios. So after watching all 3 parts, you'll get a very good understanding of how you can implement odometry in your FTC teams to leverage it in your software and overall help you win competitions as a whole. For starters, I wanted to go over current problems teams are facing and the problems that this Odometry series is looking to address. For starters, in autonomous, many teams try to take the trial and error approach where they keep tweaking time-based commands on their robot to accomplish tasks. However, this leaves teams with an inaccurate robot because the practice field and game fields are sometimes off just by a smidge. Additionally, having this method is a long process and sometimes it means teams don't have enough time to implement their autonomous in competitions. Secondly, looking at teleop, many teams find it challenging to drive the robot when it's rotated. This is difficult because drivers have to adjust their mindset to match the robot's perspective, leading to confusion and less precision control. Those are the 2 big problems we're looking to address using this Odometry series. Now, who is this tutorial for? It's for beginners who are looking to advance their teleop and autonomous using odometry. Moving on, it's important you have the right hardware configuration for your robot to make this series successful. Starting off with your odometry pods. You want 2 4-bar odometry pods from GoBuilda. These have inbuilt encoders to help you find the distance of your robot. You'll need 2 of these, one for the X position and one for the Y position. Next, you want a GoBuilda pinpoint odometry computer. What this can do is it can help you find the angle of your robot because of its inbuilt IMU. Additionally, this helps take away some of the math needed in finding out your position over time. Additionally, it's important you place these hardware components in the correct location of your robot. In order to put them in the right spot, you can refer to the user guide in the description. In this guide, you'll find where to actually place these hardware components on your robot to make sure everything works seamlessly. I've also added a total of how much this system will cost for you and your FTC team. Now diving into what is odometry. So odometry is a method that uses motion sensor data to estimate the position of a moving object over time. In simple words, it uses sensors and data to find out where the robot is on the field. There's 2 amazing ways to use this. One is encoders. Encoders can help you measure the distance you travel and the rotations your wheel take over time. On the other hand, vision can help detect the April tags on the FTC field to find out where you are relative to those tags. Now looking into what can odometry do for your FTC team as a whole. The algorithm of odometry will input your starting coordinates and heading relative to the field. Then with that information, the odometry algorithm can help find your X and Y coordinates and your heading relative to the field. Now you see here that the odometry algorithm takes away a lot of the math, and that's thanks to our pinpoint odometry computer. But it's important to actually leverage these X and Y coordinates and heading in order to make our software much more advanced. So looking at the applications in FTC, one of the biggest ones is field-centric drive control. So here I'm showing a preview of how you can actually implement this on a robot. And what this pretty much means is that no matter the orientation of your robot, you can move the robot relative to the field. So if your robot is, let's just say at a 45 degrees, if you push forward, your robot will be relative to that forward location and no longer will it go diagonal in the 45 degrees. So that will make operations much easier. Then looking at autonomous, here we have field relative motion planning. So here what you can do is you can set the robot to go to any target position on the field using X and Y coordinates and a desired heading. With that information, the robot will go ahead and move to those target locations and achieve that motion. So that's where motion planning comes into. So these two are the biggest ways you can leverage your odometry to make your robot a lot more successful. Overall, in today's video, we looked at the hardware configuration needed for your robot to have odometry. We looked at the concepts behind odometry, and then we saw the applications it can have on FTC teams in teleop and autonomous. Now I'd recommend you to move on to part 2 and part 3 to learn more about how you can apply math to make your robot have odometry during teleop and autonomous. Also, if you have any questions about today's video or part 2 and part 3, feel free to leave them in the comments down below and I'll answer them as soon as possible. So thanks again for watching today's video, and I hope you move on to part 2 and part 3. See ya!